Variables declared within procedural blocks and initialized inline may be declared as static or automatic. Static variables are only initialized once and retain their value on exit from the block. Automatic variables are reinitialized each time the block is entered. It is not advised to omit the keyword static in context where the initialized variable could be either static or automatic. Some tools may assume the initialized variable to be static if declared in a static procedural block, or automatic if declared in an automatic procedural block, whereas other tools may issue a warning or an error during compilation if the static keyword is omitted before the local static variable initialization. Hence, it is best to either include the static or automatic keyword or use a separate variable assignment as shown at the bottom of the slide rather than an inline initialization. By default, any local variable declared within a task or function are static, and hence retain their value between task and function calls unless they are explicitly declared as automatic. On the other hand, if a task or function is declared to be automatic, then any local variables are automatic unless explicitly declared as static. In this example, a static variable x is declared within automatic task T1. The static variable x will be assigned its initial value of 0 at declaration, elaboration time at time 0. The static variable x is only initialized once and retains its value on exit from the task. Thus, on the next execution of task T1, the static variable x starts with the value it had at the completion of the prior execution of task T1. If variable x was declared as automatic, either as automatic int x equals 0 or just int x equals 0, then a new variable x would be created and initialized to a value of 0 for each call or execution of task T1. There would effectively be a stack of x variables, one for each call or execution of task T1. Within the concurrent executing initial blocks, the order of execution is non-deterministic for the concurrent calls of task 1 at time 5 and again at time 25. The static variable x will increment in value for each successive call to task T1. The output argument y from task T1 reflects the value assigned to the input argument a. Simulating this example in EDA Playground, observe the assignment and updating of the static variable x along with the output argument y for task T1. This can be observed via the $display statements in the log window of EDA Playground. The output y is assigned the value of the input argument a of task T1. With the concurrent execution of the two initial blocks, the order of execution is non-deterministic for the concurrent calls to the task T1 for the initial blocks. Observe how the static variable x increments in value while the output argument y from task T1 reflects the value assigned to input argument a. Although not explicitly reported via the $display statement, the value of variable v tracks the value of y as v is assigned to the output argument y of task T1 each time the task is called. If desired, these results could also be observed via the waveforms in the EDA Playground waveform viewer.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of Brian's webinar, Common Mistakes in SystemVerilog, whenever you want by heading over to our website www.doulos.com/od and registering for free. For more free tips and tutorials, visit the know-how area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.